All right. Okay. Good evening, everyone, and welcome to the Vancouver Kimberlite seminar. I hope you all had a wonderful summer hiatus, and thank you for tuning in virtually from all over the world. I would like to introduce myself. I am Katherine Landoni, a Master's of Science student working with Professor Kelly Russell, and I am the VK host for this year. I'm here with Herman Grütter, an adjunct professor at U of A, and he's actually stepping in for Barbara Scott-Smith as the convener of the VKC series while Maya Kopylova is on sabbatical. The VKC series is a series of seminars for diamond geology and other related topics. The goal is to bring academics and industry professionals together. I want to acknowledge SRK for being long-time standing VKC sponsors. Thank you so much. I know that we're pretty well versed with Zoom at this point, but I wanted to make a few housekeeping notes. Please keep your microphones and cameras off during the presentation because it will help with the streaming quality. The presentation will be about 50 minutes long, and after that, I will help facilitate the questions and answer period. So please keep your questions for the end. After the questions and answers, we'll stop the recording and move on to a more informal kind of like pub hour. So I'm delighted to welcome Herman Grütter, PhD and PGEO. He is, I actually can't really see my notes, so I'm gonna end this presentation. I'm gonna read a little introduction on Herman. So he is a technical numerate geologist with 30 years of senior mining, junior mining, consulting, and research and development experience. His commodity specialist, chief geologist, and VP level credentials reflect value accredited geoscience practice in global rough diamond and porphyry copper gold projects. He has extensive knowledge of diamond projects and operating diamond mines and provided M&A supportive technical opinion or oversight in 3 diamond asset divestments transacted at $17 million, $500 million, and $107 million. Herman has an academic quality publication profile across the range of applied mineralogy, petrology topics, and is a long-standing adjunct professor in geosciences at the University of Alberta. Herman is currently at SRK Consulting in Canada, and he will talk to us today about lows and highs in contemporary microdiamond data. So the floor is now yours, Herman.
Yeah, thank you, everybody, and thanks for attending. It's a privilege to talk to an audience like this. I'll just share my screen here to start the talk. Find the right one. And if somebody can just tell me that they can see the screen, PowerPoint presentation.
Yeah, we can.
Yep. Okay.
Yes, can see it.
Fantastic.
Perfect.
So today is the 2nd of November, and here we are. We're going to talk about some lows and highs in contemporary microdiamond data, starting with a graphic that I put up in PDAC 2019 about the growth of, I just want to hide this, the growth of microdiamond sampling through time after 2 seminal events. The first was the institution of NI 43-101 version 1 by Canadian regulators as a result of a gold scam. And that basically forced public companies to declare material results. Soon afterwards, the Canadian Institute of Mining and Metallurgy put out guidelines for reporting of diamond data in root 2 sieve size thresholds. And the combination of those 2 events then created a forum for public reporting of material microdiamond results. And the blue curve shows how much of that data just came into the public domain soon after that. I mean, it's absolutely astonishing. And if you do what I have done, and which I reported at PDAC in 2019, you can combine this microdiamond data with subsequent bulk sampling results, which are indicated in the bar graphs over there. And you can end up making what are called macro-diamond benchmarks. And what these things are they're displayed on a grade size plot, which is the plot that you see on the left-hand side there. The y-axis is the assay counts per ton. Some of you will notice that there is no unit interval normalization in here. So I've purposely removed that because it can create a whole lot of aberrant issues because people are not necessarily paying attention to what unit interval they're using. So I've removed it, and we're now looking at raw counts per ton on the y-axis. The x-axis covers the range in microdiamond to macrodiamond weights from a sieve size of 106 millimeter, 0.106 millimeters, which are 106 microns, right up to 10 carats. And that's 6 log orders on the x-axis and 8 log orders on the y-axis. It's not often that geologists work in log-log space. It's the domain of astrophysicists. And it took me a while to get to know what sort of errors you incur in a small movement in the space as a result of not paying attention to your data. So a lot of what I'll be talking today is what you actually gather from paying attention to your data and how that is represented on this graph, this grade size plot. The grade benchmark is basically a congruent micro and macro diamond data set, which has a known recovered grade. It's not a theoretical grade. It's not a model grade. It doesn't depend on a size frequency distribution assumption. It is the data as recovered and as reported. There is one central assumption, which is that the mixture of diamonds is homogeneous. And we will look at the breakdown of that assumption later on in this current talk. At the time when we put this out in March 2019, the 30 benchmarks we had covered the grade range from 3 carats per 100 tons to 6.8 carat per ton, which is the grade of Argyle. And it was based on public domain data collated to the end of 2018. And I just have to remind everybody, you cannot recover a fraction of a diamond. So the count rate thresholds that you experience on the y-axis, it occurs at 1 stone per sieve. And we'll see what the implication of that is. So there's your 1 stone per sieve in 8 kilograms, 200 kilograms, or 1,000 kilograms. And you can see that there's a log order decrease in sensitivity or increase in sensitivity as you go to bigger sample sizes. And we will look at sample size effects a bit later in the current talk as well. So the talk today will outline, the normal case, and we will look at windspear data from 96 to 99 from the Snap Lake system, and then introduce this thing called the central limit theorem. And then we'll go on to the real meat of the talk, the low count microdiamond data. We'll look at some stuff from Fort Ellicott, Dizzy and Duke, and then also 148 and 140, 141. And this is the impact and the prevalence of these low count results, 0, 1, and 2 counts. What does that mean? And then later on, we'll look at a combination of low and high count microdiamond data. There's a very good example from the Tuwawi Kimberlite up in Baffin Island, and then the resolution of microdiamonds in parts per trillion. And then locality X, where we see a combination of both low and high counts. What we have to start off with is something like this. This is what comes in the public domain in terms of microdiamond results. In this case, I've just taken the most recent results released by Arctic Star. That's Buddy Doyle's company. They're exploring in an area east of Ikadi and north of Diavik, where they're looking to find something of value. and they're using microdiamonds as an approach. And it's an approach that Buddy Doyle has spent a lot of time working in. This is what you see in the public domain. You see a summary of microdiamond results aggregated to a total sample weight. And so I'm going to put on my little laser pointer here, the sample weights. And here are your stone counts by sieve size, starting at the smallest sieve, that's 105 microns square, up to 1.18 millimeters square. And there's typically there's a drop off of counts as you go to the greater sieves, and you hit zeros and ones somewhere up in the coarser size fractions here. What you don't see in these results is the detail of how the microdiamonds vary by 8 kilogram alicot until you get to your total sample size. And it's looking at those kind of variations that actually informs the nature of this talk. So I'll show you some of those. So let's start. We'll look at the early Snap Lake data. This is from Winspear, 96 to 99. They put this into the public domain, and they used a 0.3 millimeter square mesh bottom sieve cutoff, which these days people use 74 microns or 106 microns. But at that time, they were using a 300 micron square mesh bottom cutoff sieve. Interesting, in the early days, 96 and 97, they were taking surface samples. That's indicated in the blue diamond symbols. And most of their sample sizes were less than 100 kilos. And some of them were considerably less. And you can see that there's quite a lot of variation of contracts, diamonds per ton in that data set, 96, 97. Then in 99, they launched a mini bulk sampling program. And together with the mini bulk sampling program, they took microdiamond samples. And the weights for those samples were, again, there were quite a few under 100 kilos, but they were then stepping up into somewhat bigger samples, over 200 kilos per microdiamond sample. That's in 99. And then in response to an unsolicited offer, in August 1999, they announced something called the Value Recognition Program, where Randy Turner ordered in, I think, 3 or 4 drills, and they started drilling the Snap Lake system substantially and sampling it in a big way. And because Snap Lake actually varies in thickness, it's a dike system or an inclined sheet system. It varies in thickness. You get a different sample weight across the intersection that you drill. And so they, in 99, they collected both very small samples, down 10, 20 kilograms per sample, all the way up to 350 kilos per sample. But that's a continuous data set, and it's drilled into the Snap Lake system. And so it's a very valuable data set to look at. What do you see in terms of contracts from one system as a function of sample size? And you can do some statistics on this. If you average out everything below 50 kilos, then you get the orange average with 1 sigma variation around it, as indicated there. Between 50 and 100 kilos, you get a similar average, but with a lower variation. And then if you average everything above 100 kilos, you get the orange data point over here. That one over there, with a substantially reduced variance. And so we can see from this data set that with increased sampling, your mean diamonds per ton remains basically stable, but the variance decreases. And that's, it's intuitively obvious, but it's useful to see that in real data, this actually occurs. Some of you might look at this lot and say, well, that's a bell curve sitting or a normal distribution that's flipped on its side. And you wouldn't be wrong in making that determination, because what is going on here is this sampling pattern is basically affirming something called the central limit theorem. And this thing underlies a whole lot of what we do in microdiamond sampling. So what is the central limit theorem? There's the central limit theorem in pictures. It says in very simple words, as the sample size increases, the distribution of sample means approaches a normal distribution. Now, we can look at these four size distributions if you want on the top here. If you start with a normal size distribution and you sample it twice or 5 times or 30 times, you'll end up with a normal sample distribution. That's very straightforward. If you start with a uniform sample size frequency distribution and you sample it twice, 5 times and 30 times, you also end up with a normal size distribution or a normal distribution at the bottom. So you go from this to this after 30 rounds of sampling. The one that's kind of a little bit, and that's also sort of fairly logical. We can see how that happens. The one that's kind of counterintuitive is this distribution over here. How can you sample a parabolic distribution and end up with something like that at the bottom? So I've just taken that one. I've taken another example, just straightforward from the literature, and basically giving you a partial explanation of how this happens. You start with a parabolic distribution of population that looks like this. If you sample it twice and you average those samples, you will end up with a distribution that looks like this, to which you can fit a normal distribution. It wouldn't be a particularly good fit, but you can fit a normal distribution to this set of data over here. However, if you take the same population, you sample it 4 times, this is what your sample means will look like. And now we can see that a normal distribution fits quite a bit better, surprisingly, quite a bit better if you only sample it 4 times. And if you sample the same population 15 times, the sample means will have this distribution. And this can be fit with an extremely good fit by a normal distribution. In other words, you start with something like this. Whoops. Start with something like this at the top right here. If we sample it repetitively, we end up with a very predictable normal distribution. And you can also constrain the variance around that distribution, 15 times sampling. What does this mean in practice? In practice, this means a robust microdiamond sample is 20 to 30 samplings of the aliquot size, which often is 8 kilograms. So it's in the range of 160 to 240 kilograms. And that's not such a big sample to take, and it's not too expensive to process. And so as a result, microdiamond sampling has become kind of a mainstay of the industry these days. And what does that look like in a well-behaved data set? So here's a well-behaved data set, and it's broken down by its 8 kilogram processing units. So that's what these caustic fusion labs, they process 8 kilograms at a time. In this case, there are 24 times sampling of 8 kilograms with a microdiamond result that goes with each one of those. Right? What you'll see in the public domain is this bold result at the bottom. It's the average, or it's the aggregate of everything that's been analyzed. What you don't see in the public domain is the variation per 8 kilogram aliquot. So if you look at minimum or maximum counts in per sieve or total counts, then you can see how that varies statistically if you get given access to these 8 kilogram results. And in this case, the variation is a minimum of total microdiamonds of 51 per 8 kilogram to a maximum of 87. You can do the averages, and that's what you see summarized in the bottom here. The mean plus minus standard deviation, 73 microdiamonds plus or minus 9. which is a 1 sigma variation of 12%. There are no low count or high count aliquots in this set of data. There is a natural variation of counts in each sieve class. In other words, it's a well-behaved data set. You can repeatedly sample this particular kimberlite, and you will repeatedly predict how much you will be able to get, right? So this is ideal for statistical analysis and macrograde estimation. And I just want to emphasize, in the public, you only see the bottom line 193 kilogram total assay result. You don't have insight into the uniformity of this data set and the power of the central limit theorem as it underlies the statistics of these count rates. And so what do we do? What do we obtain when we do actually do our macrograde estimation using this bottom line data set, total count data set at the bottom here? And I just want to highlight there is one diamond in the 1700 micron sieve class over here. You'll see that diamond in a moment. This is what we obtain. That's the black curve, is the data set we just looked at 8 kilogram level. 24 by 8 kilograms, 192 kilogram sample yields a smooth grade size curve in black. You can compare it to other benchmarks. And as a result of that comparison, you will be able to predict the grade extending into the coarser diamond stones, coarser diamonds over here of 1.5 plus or minus 0.3 carats per ton. That's plus or minus 20% variance at 1 sigma with a 1.18 millimeter bottom cutoff. And remember that single diamond sitting on a 1700 micron screen? Well, that's it right there. That's one count in 200 kilos of that one diamond. It doesn't look unrepresentative. In fact, that one diamond that was recovered looks entirely representative and consistent with the rest of the benchmark curves that you see over here. So it's not necessarily an outlier. So that's the world when it behaves itself properly. And that's why microdiamond sampling is so prevalent in the industry today. It's a very powerful way of constraining your macrodiamond grade distribution from a statistical and just a practical point of view. But now we are in for something completely different. And that gets onto low count and high count results. And we'll start that conversation by looking at microdiamond results from a kimberlite called Duke. It occurs immediately east of the Fort Ellicorn, the main Fort Ellicorn province. And it was drilled into by Forest Gate Resources and sampled. You can see the microdiamond result that they put out over here. And there are some notes that go with that result, because once again, it's a single aggregated result for samples that are over 200 kilos in weight. First of all, it was processed at SGS Lakefield. They use a caustic fusion process and 8 kilogram aliquots. And so if you look at this first result over here, drill hole FG0508, that's 252 kilograms. That would be 32 aliquots, and they recovered 8 stones. There they are. In other words, 75% of the aliquots had no stones per 8 kilogram aliquot. No microdiamonds were recovered in 75% of the material that was processed. You can do the same calculation for this. For the next result that's listed in this news release, and you end up with 40% of the 294 kilos of material processed reported no diamonds in the 8 kilogram aliquot. Nothing whatsoever, zilch, nada. And it's not an isolated occurrence that you can get these zero count results. Here's another example from the same company, Forest Gate Resources. The same season, they drilled another kimberlite called Dizzy. They released this microdiamond result, these microdiamond results basically a month after the previous one we just looked at. And in their news release, they put in what I've highlighted in orange, 14 of the 29 diamonds, including one macrodiamond, came from a single 110 kilogram sample of indicated mineral-rich kimberlite breccia found in drill hole FG0514. This is drill hole over here. Okay, so now we need to do some, add some notes. Again, treated at SGS Lakefield, 8 kilogram aliquots is what they use. And we can now break down this whole FG0514 into a breccia component, that one over there, which is described over there, for which 110 kilos would be 14 aliquots, in which 14 diamonds were recovered. There they are. So average of 1 stone per 8 kilogram. The remainder of what came out of this hole is 321 kilos. That's 40 aliquots with 6 stones. So 85% of the remainder recovered 0 microdiamonds per 8 kilogram aliquot. And again, similar sort of calculation for this one over here, 80% of the material that was treated reported not a single microdiamond for 8 kilogram aliquots. So the point I'm trying to make here is that on the low count side of things, the number 0 pops up with substantial frequency, and it's something we need to deal with when we look at these kind of microdiamond data sets. So let's go look at it in a big way. Here's a summary done by Sean Harvey, 2004, public domain. Synthesis of diamond recoveries from the whole Fort Alacorn Kimberlite province. I want you to focus on this column called stone density. It's marked in the orange arrow over there. A stone density of less than 125 stones per ton is basically less than 1 stone per 8 kilogram, and less than 1 stone per 8 kilogram is exactly 0 stones per 8 kilograms. So all of these kimberlite bodies have been sampled. Here are the sample weights, and the ones that are in the orange boxes, all of them have less than 125 stones per ton recovered. In other words, all of those kimberlites are reporting 1 or more, in some cases all, of the results with aliquots at 0 stones per 8 kilogram recovered. What does that do to your data set? So the impact of these 0 count and low count, specifically 0s, 1s, and 2s, is that they introduce discretization in your and step changes and null discontinuities in your data set. And they create very high variance at low counts. In other words, it becomes rather noisy, and typically in coarser sieves. It's very difficult to reconcile the fact that you can sample 350 kilos, roughly over here, and get almost nothing. And then in other places, you can sample 300 kilos and get substantially more. This area of the data set in the Fort Alacorn province that's below average 2 stones per 8 kilogram over here, the bottom, all along the x-axis over here, that's a very problematic part of microdiamond data sets, and we will see why in a moment. We're still going to stay with the Fort Alacorn examples from the same report by Sean Harvey, because it's free. Here's a table, and I'm not going to give you any of the details of this table, but it's microdiamond data from the 148 kilo kimberlite at Fort Alacorn. This is what it looks like on a grade size plot. Now, I've changed this grade size plot a little bit. I've changed the scale. It stops at 0.5 carats. It doesn't go up to 10 carats. And I've put in select micro macro benchmarks. All of them are less than 76 carats per 100 tons, or 0.76 carats per ton grade. That's the colored curves over here. These are the benchmarks. And then in black, there's all this data that's in this table plotted out in increasing stone size and at the count rate reported in this report by Sean Harvey. So the observation to be made is that where we get into these zeros, ones, and twos in the coarser size, coarser sieves reported, that's this green window over here. You can see that these curves of diamond counts per sieve size, they're becoming quite noisy in this part of in this green window. And it's actually very difficult to confidently project where these black curves will end up projecting relative to the benchmarks. Are they going to fall short over here? Or, I'll switch on my laser. Are they going to fall short in this area over here? Or they're actually going to continue in that area over there, which is a major difference in grade potential for these different, for the Fort Ellicorn kimberlites. So what we're trying to do here is we're seeking accuracy on the 425 to 850 micron sieves at count rates of 2 to 60 stones per ton. So there's 2, bottom here, that's 2 stones per ton. There's 60 stones per ton, that's 1 in 16 kilograms, and this is 1 in 500. And so those are the resolution thresholds that you're trying to achieve. To achieve them, one of the things you can do is you can increase your assay aliquot size to achieve resolution within that green window. You can increase your assay aliquot size from, say, 8 kilograms to 24 kilograms. And then the central limit theorem says to you, well, you have to take 20 or 30 times 24 kilograms. In other words, your microdiamond sample weight is going to be in the range 480 to 720 kilos to obtain resolution of what happens to that curve inside the green window. And we'll all notice that the sample sizes that were taken in the event and that are displayed on the right-hand graph, none of them are even close to 400 kilos. And so if you want to resolve this type of situation for the Fort Ellicorn kimberlites, this is the type of sample size you need to get to. I'm going to go back here. Don't blink now. I'm still going to stay with Fort Ellicorn. I'm going to jump to the 140, 141 kimberlite. Here it is. Let's do that again. You can all see what's happening here. There's the same green window. We're recording zeros, ones, and twos in the sieve sizes above 425 microns. That's them over here in the green window. We can follow these, the size frequency distribution of this data for 140, 141 public domain data. And when we hit this point over here, it seems like we would want to project it going down in this direction. In fact, many models will do that to you. You will have to ignore this stuff as being noise. In fact, very noisy. But we've just made the argument that you can remove that noise by increasing your sample size to things that are in the vicinity or upwards of 400 kilos. So here's the general statement. This discretization that we see into zeros, ones, and twos is actually very common in lower grade settings, which is what Fort Ellicorn is all about. And if you're in the business, you have to figure out the risk versus reward for additional microdiamond sampling at about 400 kilos per lithological domain I don't think it's a big problem. 4 domains at 500 kilograms each is 2 tons for microdiamond assay to support your development of your project. And that's a whole lot cheaper than bulk sampling. It's an eminently achievable thing to do, and you can get resolution within that green window that's so critical for lower grade settings. So, with that in mind, let's go have a look at the Tuwawi kimberlite, because it's a very interesting microdiamond data set that has come into the public domain from this kimberlite, because very big samples were taken from Tuwawi. So first off, this kimberlite was discovered, I think, by Kennecott, Canada. They drilled 4 holes into it, and they took 1.5 tons of kimberlite core. There we go. And produced microdiamonds from it. This is the microdiamond result that became, got into the public domain in 2003. They then let go of the kimberlite or the concession, or they optioned it to Randy Turner of Diamondex. And in 2008, Randy Turner had put in 12 holes for a total of 1,300 meters and sent 2.8 tons for microdiamond processing, of which 1.9 tons over here is reported in the public domain. We got 396 stones larger than 0.15 millimeters. But what I want to draw your attention to is they didn't, not only did they take large samples, total weight of almost 2 tons, they have elevated counts on small sieves, these guys. And then they have these persistent low counts on larger sieves, these guys. 1s, 0s, 1s and 2s, the occasional 5 and 4. And this is a very big sample. And it's a repeat result by 2 independent operators and on the same kimberlite. Not very often that you get the privilege of speculating on what's going on at Tuwawi. But this is what it looks like on that same grade size plot that I put up for $4 corn, just for reference so that we can keep it constant. In blue is the Kennecott, Canada exploration data set dated 2003, 2004, and in black is the Diamondex data set dated 2008. So what do we see? There's the same green window. These people have sampled in their large samples. They've actually provided continuity of diamond assay through this green window where you need to resolve things with large samples. They've taken multiple large samples and proven that it's tenable to do so during exploration. And they did it during the exploration phase, but it's also useful to do that during a project development phase if you're dealing with lower grade kimberlites. Both of these operators recovered 0.3 millimeter stones at 6 to 9 parts per 10 to the 10, implying that recovery of 106 micron stone microdiamonds, these ones over here, is feasible at 1 part in 4 trillion. These are the kind of resolutions that are achievable, and these data sets prove that it can be done repeatedly. So ultra low microdiamond count rates, less than 1 stone per ton, are resolvable. Here you can see there's the red line for 1 stone per ton, and these data go below that on a log scale. You just need to use appropriately large samples, and it's not impossible to do so. In other words, microdiamonds can provide excellent support for grade continuity in mineral resource models. But all of us can look at these results from Tuwawi, compare them to the benchmark curves and say to ourselves, well, what gives? It doesn't look like we're actually getting something that would correspond to a benchmark. So let's look at that in the next slide. Here's the data. This is what I think is going on. We're actually dealing with two different populations of diamonds in Tuwawi. Diamond population number 1 is outlined in this orange curve over here. It would come from something like this diamond peridotite nodule or xenolith, which comes from Udachnaya. It's labeled U331. This piece of the mantle contains 30,000 diamonds. All of them are in the size range 0.02 to 0.7 millimeters. This piece of rock weighs 10.5 grams, and the macro grade, in other words, the material that's bigger than 1.18 millimeter, is 0. So this piece of rock contributes a huge amount of very small diamonds and nothing in terms of commercial diamonds. If you dilute one of these in 95,000 parts barren kimberlite, you will end up with this orange curve. The other part of this diamond distribution that we're looking at on the grade size plot is a second population of diamonds that was recovered by both operators at Tuwawi. It looks like it comes from something like diamond eclogite U51, also from Udachnaya. This piece of rock contains 30 diamonds in the size fraction 0.8 to 3.4 millimeters in 125 grams. The macro grade of this piece of rock is 20 or almost 28,000 carats per ton. And you can explain diamond population number 2 by 1 part U51 in 140,000 parts barren kimberlite. In other words, at Tuwawi, we're not dealing with a homogeneously mixed diamond population. These diamond populations are still discrete, and we are detecting them as discrete populations, and they're not homogeneously mixed. And the key with Tuwawi is realizing that there are these nuggets, extreme nuggets in diamond concentration that are basically being diluted in barren kimberlite. So I think I've spoken about that. The point about the current benchmarks that we've compiled from public domain data is that they implicitly assume homogeneous mixtures. And you can describe those by a single grade size curve. But the Tuwawi data upends that assumption and instead forces us to think about a more conventional explanation that's founded in where the diamonds ultimately come from. You see, I'm getting towards the end of my talk here. I said the title was Observation on Lows and Highs in Contemporary Microdiamond Data. I'm starting here. This is a summary of a microdiamond data set. It's summarized by 8 kilogram aliquot. So it provides you with the detail of what's going on in this data set. 72.2% of the data of the 8 kilogram aliquots report no microdiamonds whatsoever, larger than 1.106 microns. 13.9% has 1 microdiamond in an 8 kilogram aliquot, and so on, up to 13 microdiamonds per 8 kilogram aliquot. So there's a lot of zero counts, there's a high proportion of low counts, but I'm not finished. The same data set continues. It goes to 16 where there's 0 counts, and then all the way up to, when you step all the way up to 30 microdiamonds per 8 kilogram aliquot, 31, 32, 37, 53, 72, and 312 microdiamonds in 1 8 kilogram aliquot. So the summary of this microdiamond data set is 72.2% of the sample weight is barren. 26.7% has low count, microdiamonds in it, and a total count of 722 microdiamonds. And 1.2% by weight contributes these higher count microdiamond results, a total of 685 microdiamonds, but only from 1.2% of the rock. So this data set again demonstrates to us that all our diamond assays reflect mixing of two physical components. You can call the one KM, that's a barren kimberlite magma, that's the ultimate low, that's the thing that can give you zeros. And we know that it has to be the ultimate low because we can never prove that kimberlite magmas actually precipitate diamonds as a phenocryst. In fact, the opposite is likely true, that kimberlite magmas regularly resorb diamonds. So that's the ultimate low in any microdiamond data set, is the fact that the carrier is a diamond averse. The high is the diamond-bearing mantle component. These xenoliths, they can occur as nuggets. And so our ability to estimate macrogrades from microdiamond assays is determined by the size frequency distributions of the diamond-bearing material. Those are the xenoliths that we've seen have to explain what's going on at Tuwawi. And they end up as mixed size frequency distribution nuggets. If they are not homogenized throughout the medium that you're sampling, you're going to get nugget effects. And those nugget effects are most pronounced at low grades. So the homogeneity of diamond material mixing in the kimberlite magma is an important aspect of how we approach these data sets. Bear in mind that everything that you see in kimberlite is diluted by a factor of 10 to the 5 in terms of diamond concentration from its source. And so the amount of dilution is a very critical component in how we view the data that we collect for microdiamonds. The extent and size of sampling, we've gone over that. That has to do with this very counterintuitive thing called the central limit theorem, and how it works in your favor as you repeat sample things at decent sample sizes. Assay resolution is actually not an issue. The microdiamond labs that we have available to us commercially today are fully capable of reproducing microdiamond results at 1 part in 4 trillion. That's pretty astounding to realize that this is what we're actually dealing with. And we need to start looking more carefully at our data to identify and differentiate great size curves for heterogeneous mixtures. In other words, use of 2 or more benchmarks and not simply fitting everything with one great size curve. So that's the end of the talk. I have to put in some time for acknowledgements, because I have to say that the support that I got from BHP Billiton, their Minerals Exploration Department, 2004 to 2012, was instrumental in my view of how we use microdiamonds in the industry, and the way that they rolled out an embedded microdiamond sampling strategy at 200 kilogram weight was quite instrumental into my view, the view I started developing about using this technology. But then there was also another seminal event which occurred in October 2010. And while I was still with BHP, and it occurred because Peregrine Diamonds introduced something called the Hornet RC rig into their exploration program. This is a little Hornet rig. It's driven by compressed air. You end up getting a dry, sandy product. a cyclone over here, and on a good day, we could drill palsy. So, because we had to ask ourselves these questions. If you use per kilogram, then if you use the caudal. Are the diamonds fragmented by the hammer? That is, yes, it is. Does diamond return, in other words, in its way up? I don't think so, but I've never really tested that in a big way. Does the cyclone that's sitting on the end of this air blast, does it fractionate or concentrate microdiamonds? Notice the cyclone has two ends. It has the bottom end over here where the coarser sample product comes out. And it has a top end, which is a chimney where all the fine material sort of disperses into the air. And it turns out this cyclone does actually do stuff to microdiamond concentration, much as a dense media cyclone, a dense media separation plant does to diamond in a normal recovery plant. And finally, we needed to answer this question: what size weight of RC sample must be collected to constrain a grade potential of around 0.5 carat per ton to within plus or minus 30%. And just by going through these questions with Peregrine, I learned a huge amount about what we need to be doing with microdiamond data sets. So I'm eternally thankful for Peregrine for bringing this little beast onto their project. And then also Jennifer Pell for sense checking of all the public domain data that we aggregated. She was also the initial stage research collaborator. And currently Cliff Revering is my SRK colleague and sounding board when we talk about microdiamonds and macrodiamonds, and then some SRK clients who remain anonymous, who provided me access to aliquot level 8 kilogram data. So thank you very much, everybody.
Thank you, Herman. Very statistically sound. So now we're going to move on to the questions and answer period. And you can either send a question in the chat and I can read it out, or you can unmute yourself and or turn your camera on and ask Herman a question. So I'll turn the floor over to the audience now. You're getting a lot of emoji applause hands in the chat.
Hey, it's Tom McCandless. Can you hear me?
Yeah.
Yeah, I can hear you, Tom.
No camera, sorry, but just a question. It's really good. Thanks, Herman, for a really well-organized presentation. I really appreciate that. One of the parameters that we've looked at is the sampling itself. How do you feel about how sampling is done these days, and whether sampling, say, of a particularly heterogeneous kimberlite by someone not that well versed in understanding the representability of sampling it over, say, the De Beers approach of sampling every other few meters, or a lot of people do it that way. What do you think about that potential effect in the very first stages of data collection?
Yeah, look, so it all has to do with what's representative, right? In well-behaved systems, like the one I discussed in the beginning, it basically doesn't matter where you take your 8 kilogram sample. Right, that's a well-behaved system. It's well mixed, and so as long as you're within your one domain, any 8 kilogram sample will do. And as long as by the central limit theorem, you end up with 20 to 30 of those 8 kilogram samples, and they're distributed representatively through that domain, it looks like you're good to go. And the basis of the way we look at microdiamonds is exactly that type of sampling program. Things get a little bit more complicated if you're dealing with that there is grain size differentiation in kimberlite. It's just like, what does the grain size do through a DMS plant? It's the same problem. My advice to clients has been to start increasing the aliquot size. In other words, I've actually advised some clients to take 56 kilograms, so 7 times 8. There's no between one sample in a piece of core, and the end of another. So it's a 56 kilogram continuous sample. And then that starts to smooth out all the variations that you're trying to limit in these heterogeneous media that you're sampling. I don't know if that answers your question, Tom.
Yeah, it didn't. It raised another one, so it's okay with that. But and you're breaking up just a little bit on my computer, so apologies if I didn't clearly hear your answer. But it sounds like that to increase the aliquot size, you're really, because of the physical limitation of the cauldrons that are used by bulk fusion facilities, you sample over a longer linear unit of, say, core length for microdiamonds. Is that correct?
That's right. Yeah.
Okay.
So great. That the argument cannot be made that 56 kilogram sample has somehow missed something. You've sampled all 56 kilograms and it's continuous. So whatever is inside that length of core that you've sampled at 56 kilogram unit size, you've got it in your sample. The argument cannot be made that you've missed something.
Yeah, but does that not bring in the possibility of, if you, depending on the level of the logger, if that isn't one domain that you've sampled across domains, within that 56 kilos, do you still take an 8 kilo from 2 and then aggregate them so that you can sort that out if you find you've made a mistake in the logging?
Yeah, you can. Yeah, I mean, obviously you record the 8 kilogram intervals, but you aggregate them after processing at, say, the SRC. You aggregate them together into 56 kilogram units, and I can show you. I can show you the difference that it makes in the variability. It's insane. If you consider that same data set at 8 kilogram aliquot size, you become subject to the 0-1 effect all over the place. And you literally look at noise. But if you take it, if you aggregate the results into 56 kilograms or 64 kilograms or 74 kilograms or 72 kilograms, the variability just goes through the floor. And you can actually start using the data in a statistical way. I've done it a couple of times, and it's astounding how different the variance envelope is.
Yeah, no, that makes sense, but I think it's really important to record the from 2 at the 8 kilogram aliquot level.
Yeah,
because you're not always right when you're doing the logging.
No, absolutely. I mean, you have to anyway, in terms of just sample assurance, right? And chain of custody.
Does anyone else have any questions?
Yeah, just John Bristow to Herman. Thanks, Herman. That was great. I mean, just you obviously haven't had time, but with the work you're doing, and you see all that miles of core laid out or kilometers of core. I mean, obviously you're looking at all the other petrographic mineral chemistry and data. So there's a whole lot of other additional support you have to this microdiamond study?
Yeah, yes and no, John. You both of us know that I started my life in petrography and I migrated through indicator mineral chemistry. So, as this microdiamond technology broke open into the public domain, my view on these other supportive data sets has become more nuanced. Microdiamonds have become so powerful that if you do sample them correctly, you can get a very powerful result, a very important or weighty result for not a lot of money.
Yeah.
And
Yeah,
the
no,
difference,
I think
and the difference is that the other techniques are qualitative and that you can use them. There are definitely circumstances where you should use them, but they don't have this quantitative predictive power that come with the microdiamond statistics. And so I've become, because microdiamonds are now so cheap to do, comparatively speaking, and they are so powerful that I've become more open to being more reliant on this technology.
Yeah, and I think we all agreed. And then the very simple sort of add-on to that is you just take, more bigger samples, which is also, effectively we're capable of doing that today with all these sort of modern techniques. And, even looking at your little RC driller, you can take it into the field.
Yeah, that RC drill was so productive that it produced more material than what we could stick into a bag. We left material lying on the ground.
Yeah, interesting. And then just statistically, your table you showed the ends with the 72, 26, 1.2%, is that worldwide data? Or was that just Canadian?
No, this is from a single, it's from a single domain. It's a client data set. They've given me permission to share it in this anonymous format, but it's a Kimberlite evaluation data set, and it's not a small data set, it's a big data set.
What, with multiple Kimberlites?
No, one Kimberlite.
One Kimberlite, okay.
Hello.
Interesting.
Hello, Steve Haggerty here.
Hi, Steve.
Hi. Hey, Herman, a great talk, thanks very much. But it seems to me, gentlemen, including John, is that what needs to be addressed is, can you please justify the origin of microdiamonds in relation to macros, okay? And it seems to me also, regardless of the volume of material that you're taking, yes, you're going to get big ones, you're going to get small ones, but let me remind you, please, that the log normal relationship with ants and eggs, ostriches and eggs, impact craters, it's a log normal distribution. It's a log normal, basic, universal law, okay? So my question, please, gentlemen, and Herman in particular, it seems to me, if you're really going to convince people outside the scientific community are not in agreement with you. I can tell you that right now. Secondly, it seems to me if you're really going to convince people, what you're looking at is a few cores, okay, in terms of the hundreds of thousands of tons of materials that have come through the mantle, that have traveled, taking diamonds from the deep earth, from the lower mantle, through the transition zone, into the subcontinental lithosphere and up there. How the devil can you possibly look people in the eye and say that this is the distribution when you're looking at pinheads and tell them what the final distribution is going to be? Yes, if you crush a big piece of ice, it's going to go into smaller pieces. It turns out, you know what? It's log normal. So it seems to me that what needs to happen to make this legitimate, to make it advance, to make it go forward, you have to convince us that you know how diamonds are formed and you know where the microdiamond population comes from. There is no, for example, relationship between microdiamonds and macrodiamonds in terms of carbon isotopic compositions. So I plead, you know, as far as I'm concerned, and I don't want to use the word, but I'm going to, it's a sham. And I think you raised the point very carefully initially, Herman, is that we really don't know, and we really ought to be careful. As far as I'm concerned, it doesn't matter how much material you concentrate, there's absolutely no way that you can relate small diamonds to big diamonds. That's it. Thanks. Great talk, Herman.
Do you want me to make a comment, Steve?
Oh, I would hope so.
Look, let me just share my screen again if I can find. Oh,
You are still sharing it.
I'm still. Can you see the Tuwawi?
Yes.
Yeah.
The background.
Yeah, the small one, 30,000 stones, sure.
Yeah.
I think that, I mean, that you know, that is a plea to wanting everyone to understand what the relationship is between big stones and small stones. You've answered the question, Herman.
Yeah. Look, I mean, it's not that difficult, Steve. The key to the log normal distribution that's been used throughout, you know, the size frequency distribution, the discipline of grade forecasting, is that you get these components mixed thoroughly. If you do not mix them, you see them in their original state. And so that kimberlite magma that travels to surface.
It's not a magma, for God's sake.
Look,
There's no way that it's a magma.
call it a solid.
Whole bunch. It's a whole bunch of materials that come out. And for God's sake, if you believe that there is a kimberlite magma down there that brings up the diamonds, for God's sake, Herman,
Call it a soliton then. It's a solitary wave. The solitary wave that makes its way to surface entrains this material, and if it does not mix this material,
it's not going to mix.
You will end up with diamond size frequency distribution curves like the one we've seen at Tuwawi, repeated twice by two independent operators. And that's a signal that you can go to the research that Derek Robinson did on eclogite xenoliths from Arapa that's sitting in his PhD thesis, where he basically says exactly the same thing. That's how long ago this piece of information has been floating around.
Well, that's the point. It's a long forgotten piece of information that clearly does not have any 21st century scientific basis, period.
But Steve,
I've looked at, and I've talked to Derek, I talked to Derek Robinson long before he passed away on exactly the same issue, okay? And you know what? He admitted, I can, not only that, I have a document to show from Derek Robinson, a big, beautiful diamond that I picked up in Jagersfontein. What a beauty, what a mother, Steve. We talked endlessly about the situation of trying to predict microdiamonds to big one. And you know what? He had some doubts.
Steve, I think there's are you talking about using microdiamonds to correlate to type 2 diamonds?
No, you are.
No, I'm not.
Okay,
This whole
wait a minute. What's the cutoff point then? Are you just talking about microdiamonds to small diamonds?
Steve.
Fine, no problem. Then don't go beyond 1 carat.
Steve?
Yes.
This whole microdiamond enterprise is based on recovery of type 1 diamonds. The moment we start talking about type 2 diamonds, everybody acknowledges.
For God's sake, you're talking about diamonds, you're talking about size distributions, you're talking about big guys versus small guys, small craters versus large craters, small eggs versus large eggs.
Steve,
what's the difference?
The moment we start talking about type 2 diamonds, we're talking about the special size class plus 10.8 carats. everybody who's in the industry who actually is concerned about how to constrain that part of the diamond population, which is 2% of current production worldwide, acknowledges that you cannot use microdiamond size frequency distributions to predict the occurrence or abundance of plus 10.8 carats diamonds.
What a disappointment. Thank you, Herman. I finally understand. Thank you.
Herman.
I think you ought to have said at the beginning, my dear friend, here are the limitations. It doesn't go beyond this. Here are the diagrams. That's a limitation. But you know what, Herman? I get called up once a week. Can you please tell me and please make a prediction in terms, and the answer is no. But I think you've answered my question. Thank you. You cannot go beyond 1 carat to 1.8 carats. That's it. Thanks.
Yeah, look, I'll refer you to a talk by Evan Smith.
Yes.
Where he says that you can clearly see at the GIA when you hit the specials class plus 10.8 carats, you can see that it's a completely different population of diamonds than type 1 diamonds. And his talk is in the public domain.
Yes, I've heard it. I was there, sure.
You know, he's got several different talks around type 2s, but this particular talk, he actually opens the book on diamond populations as they observe them at the GIA. And he makes the point that the moment you step into 10.8, it's a completely different population. We now also know that the genesis of those diamonds is completely different.
Yeah, Herman, if you go back to the original work, you know, done by De Beers and Tinas and that, I mean, you know, we didn't even know about sort of big diamonds back in those days.
Well, you did, but you didn't take advantage of it.
Well, Steve, I think to be quite honest, we didn't because, well, they all got broken, Steve. I mean, that was the problem.
No, you knew about Cullinan. Come on. You knew about the Excelsior. You knew about the Excelsior from Jagersfontein. Come on.
No, sure. No, but no one actually sort of
knew
figured
about
out
the big diamonds coming out of India. Come on, John.
Steve, no one actually sat down and worked out, you know, where exactly they'd come from. As Herman says, you know, it's only more recently that we've realized that they're another population. But in the days of, you know, early days of exploration, it was a case of, you know, what, and that's been the success is, you know, we needed a tool to show that we could very quickly evaluate lots and lots of kimberlites. But I mean, I think we all agree, Steve, is that the case that, you know, there is, whatever the way kimberlites are in place, there is some sort of mixing and smoothing process on that long distance journey, 150, 200 kilometers to the surface. You know, so that you end up with a population. I mean, we see the same thing in alluvial deposits. Don't forget, you know, we also use size frequency curves in alluvial deposits, and you can see the different deposits and the different diamond populations.
Sure. No, I agree to that. My real deep concern is the lack of understanding and the lack of cognizance, the lack of connection between the origin of diamonds and the so-called size distribution. But I think Herman has adequately answered that. There's a limitation. Now, the question is, why is it limited to small diamonds and not to the size frequency distribution as it is, I repeat, eggs in ants versus eggs in ostriches. Secondly, you go back, I think I have now 25, 30, 40, 50 examples that the size frequency distribution, whether it's graduates versus economics versus anything else, the size frequency distribution, gentlemen, ladies and gentlemen, I beg your pardon, it's a universal law. There's nothing special about it. But what Herman has now pointed out is that in fact, no, diamonds are special. We go beyond that, we cannot go beyond it. Come on, gentlemen. If it's a law, then do it. It ought to be universal. It's not. And I think it's I think it's a shame, okay? That's my view.
Hi, Patrick Bartlett here. Just, Herman, in terms of what you've been talking about today, I think it's very interesting. And all the work that we did over the years pretty much corroborates what you're talking about. Something that I always found quite interesting was that at Cullinan, you've got three major intrusions, the brown, the gray, and the black kimberlite. In the brown kimberlite, we took probably 400 kilograms of sample in 20 kilogram lots. We didn't find one single diamond there over the years. And then subsequently we embarked on a bigger program of sampling, and we ended up eventually, I think, about 2.5 tons of kimberlite that we sampled, that we recovered microdiamonds from. And from that, we got enough diamonds to draw a curve. That was Johan Ferreira doing most of that work, to draw the curve. And it was the accurate prediction of what the grade was in the brown kimberlite, which was about 80 carats per 100 tons. So that was quite a lesson. We thought that microdiamonds just didn't work in the brown kimberlite. It obviously did. It was just a case of the size of the sample that we had to take. And also the other thing that I found interesting was that there was it was really only the bigger diamonds. You weren't finding diamonds in the small sizes, microdiamonds. You were finding them only in the bigger sizes. Another thing that is peculiar around that brown kimberlite, which I don't know what the real implications of it are, but the brown kimberlite did not contain any type 2 diamonds, whereas the rest of the pipe, the gray kimberlite and the black kimberlite contained type 2 diamonds. About 2% of the population was type 2 diamond. And in those other two kimberlite types, the gray and the black, everything was normal. So we went in there, we sampled, we got everything out of it, and we took literally hundreds of samples. We ended up with thousands of microdiamonds. And the other element that we've been talking about today, we also took some big samples, probably sort of 50, 60,000 tons. And it was still Ingrid Chin and Farnes Viljoen were looking at the diamond populations. And certainly your type 2 diamonds go right down into the smallest size fractions. I don't know if they go into the microdiamonds, but throughout that size frequency distribution, you do have the type 2 diamonds. They don't just disappear. I quite understand that the big ones at the top are something special, but the type 2 diamonds are there from 1 millimeter upwards. Thanks.
Yeah, no, that's a really good point, because I mean, Tuwawi showed that in the 1960s from Premier and other deposits. You're absolutely right. There are type 2 diamonds that are less than 1 carat in the micro size. Absolutely. And not only that, the carbon isotopic distribution is -5. Okay, but that's right. That's a really important point. Type 2 diamonds also exist in the micro size. Thank you.
Well, that was what we thought. We did some work on it. I don't know whether there was ever a write-up on it or not, but we were certainly looking for type 2 diamonds in the micro diamond size distributions.
Beautiful. Thank you.
Yeah. Look, if you go to Evan Smith's paper, Evan Smith's talk, he does show, and he also in his Nature paper, he does show type 2 diamonds that are smaller than 10.8 carats. There's no question about the fact that they do exist in smaller sizes. It's just that the proportion of type 1 diamonds above 10.8 starts declining rapidly. There are type 1 diamonds that are larger than 10.8, but they become successively rarer than the prevalence of type 2s at that size range.
Correct.
Where type 2s are present. Now, some of you might not know this. If you go look at Storm Diamond's website, there's an absolutely brilliant expose of the recovery of type 1 and type 2 diamonds from the coral kimberlite that they've been treating over the past 6 or 7 years. under the guidance of Debbie Bowen, who used to be the sorter at Letseng, or the diamond house controller at Letseng. And Debbie knows how to identify a type 1 and a type 2 without any additional scientific instrumentation. She just looks at the stone and she knows. That's recorded in the paper. And the other geologist who's been working with them is John Ward. They have profiled the type 1 versus type 2 populations in 6 individual intrusions inside one kimberlite pipe, to the extent that they now turn a profit out of that operation, because they know exactly which intrusions contain which type 1 or type 2 diamonds.
Oh, that's right.
Just go to the website. It's all public information. It's astounding what they've achieved.
Herman, something else that might be of interest was De Beers at Cullinan and probably at Finch as well has a huge amount of information on microdiamonds and diamond distributions. Those mines obviously now belong to Petra Diamonds. I don't know if the Petra has any interest at all in keeping that secret. If we could approach them, if you want to, I can try and approach them and ask whether they'll make that information available. I don't even know if they've actually got it, but there's huge databases there, which could be interesting.
Yeah, look, Pat, thanks for the comment, but I've been very, Jennifer Pell will attest to this. I've been very ruthless at making sure that everything that I talk about is public domain information.
Okay.
That's Jennifer was, she was instrumental in helping me and checking all the data and so on. We are, I'm resolute. I will only talk about stuff that's in the public domain already. And there is huge amounts of information in the public domain. Sure,
Okay.
Sure, the 8 kilogram level detail is the kind of stuff that's not in the public domain. And there is a lot of very useful information hidden at that 8 kilogram level. And for that, I'm eternally grateful to some of the SRK clients for giving me permission to talk about those kind of data sets.
Yeah, I'd just like to just have one more question, Herman, just to follow up on the type 2 stuff. Remember that we think about type 2s, it's a geochemical definition for type 2s in some people's minds, and it's a value definition in other people's minds. And you can certainly have type 2 microdiamonds. Talansky in the 60s showed that the premier kimberlite was dominated by type 2 microdiamonds and Finch was dominated by type 1s. So that information's been around. It's just a function of nitrogen being around where the stones form. But type 2s in the plus 10.8s carry a specific and then typically an unusual diamond shape that distinguishes them in their environment of formation. So, but anyway, that's my diamond comment. I like this slide that you still have up here, Herman. I want to talk about exploration for a minute and go back to the nuances of indicator mineral stories. So if I look at the diamond peridotite U331, I can't remember if that was a lertolite or a Hartsburgite, but it's probably got, if it's either one, it's probably got 10 to 15% of garnet in it that we would use in till sampling to look for a kimberlite that might be carrying a peridotitic diamond source. And then the eclogite U51 has about half and half garnet and E-type or garnet and CPX, which the E-type garnet will survive in the secondary environment in transport. And then when I look at the plots, if I were to think about the grade projections from the different size distributions there, you get a lower grade expectation for a dominantly E-type diamond parent rock source and a high grade but a low coarse stone size for the P-type source, DP1. When you try to translate that back into just conventional, say, stream sediment sampling and anywhere else or till sampling in Canada, is there a way to have you ever thought about trying to calibrate in your mind how you deal with, if you can, once you've identified an E-type garnet, for example, in a sample, abundance of a specific indicator in that size fraction, or that sill sample that helps you to know whether you're chasing one of these types of diamond parent rock sources or another in a kimberlite?
Yeah, look, I think John Gurney is the guy who we should answer that question, Tom. I haven't gone down that route really. What I can say was actually very, very useful both at the Churchill project and then also at the Chidliak project, and the Chidliak project result is actually published, is we found that kimberlites that carry a lot of garnets per kilogram, in other words, they're loaded with indicators, are always better to look at than kimberlites that have less, sometimes log orders less indicators per kilogram. And so we've always used the abundance of indicators per kilogram of rock, or in some cases per kilogram of till, as an indication of that's a better kimberlite to look at, all other things being equal.
Yeah, and I guess, Herman, just adding to that, I mean, that the eclogitic garnets you'd see more of them in a cold climate Canadian situation compared to, say, down in Southern Africa. And just to add to Tom's point, I mean, it was always very interesting that the Soerfer fishers, just north of Frank Smith and south of Bellsbank had a huge number of these hugely highly diamondiferous eclogites in them. And interestingly, the in situ grade was, probably for good reason, also very high. The Soerfer fishers had really excellent grades.
Yeah.
Just an observation. So just to end off, and it's time for breakfast. I mean, when's the expose now about the, the origin and the predictability of big diamond populations?
I've been working on that, but interestingly enough, not using microdiamonds.
Thank you, Herman.
Steve, how many scotches have you had now?
I'm joking. Yeah, I've been working like hell.
Okay, but thanks everyone. That was excellent. I'm sure we look forward to more about this discussion.
Yep.
Yeah, thank you for joining.
Thanks.
We do have one more question from the other John who is on the phone call. And it'll probably be the last question, and then we'll transition over to our more informal hangout, I guess you could say. So John asked, how did Herman convert the sieve sizes into carat weight per stone?
Oh, look, you can do it from first principles. You just assume a perfect sphere as it goes through a square mesh sieve. That's a very good, very good approximation of the carat weight of a stone. You can do it from first principles, or you can just measure it.
Great. I hope that answered John's question. All right. Well, I will end the recording now, and we can continue talking off the record. So I'll stop it now.